Okay, I think most of you are here, so we can start with the session. Before we start with this topic, which is a really interesting topic, um, uh, I forgot what I was about to say. Sorry, I got distracted by a text. Okay, yes, I didn't send you the illustrative life table, but what I did was that I uploaded the file. If you go to learning models and where you can find everything, in survival models, in the first learning model, there's one that says tablas de mortalidad. And there you can find two files. One is life tables 2, which is, I believe, is the same illustrative life table that we have. And that is because I had it before, like, there was a life table that I had from the beginning of the semester on Blackboard. And the second one is called ILT y tablas, bueno, ILT y tablas clase. That is the file that, well, it's not the file that we used in the last session. That is the file that I used with yesterday's section. So essentially, is the same information that we have. So you already have so you can access the tables if you just look for this thing on Blackboard. Okay. Now, let's talk about. Well, let's continue talking about life table, but in this session we're going to discuss what to do when we have fractional ages or fractional durations, which is something that we might find when we have if we have a life table. For instance, if we have the mortality model, there is no problem. I can ask you, okay, what is the probability of a person surviving half a year? And again, that is something that you can estimate without any issue because you have the expression for that mortality. But if we have life tables, and we're going to be using life tables, well, yeah, just to estimate the values at the end of the session or for the examples, we only have information for specific ages. So if you have somebody who's 25 years of age, and I ask you, okay, what is the probability of this person to survive to age 25 plus 25.5, then we will have an issue because we don't have a way to do that or a direct way to do that with a life table. This afternoon we're going to learn how to do that using the information that we have. Okay. So let me go to the next slide. So this is essentially what I just told you, is that sometimes we need or we want the information for not complete years of life or for complete years of duration. And this is going to be more common than you probably think or can imagine, but we need to find a way to be able to interpolate this information between ages. And we have 3 ways to deal with this, or 3 different approaches. The first 2 are the most common, about the common ones, and the third one is not that really uncommon, but it's more time consuming, so we usually don't go with that. But again, it's nothing like really complicated. So the first one that we're going to discuss tonight is the uniform distribution of deaths. Essentially, we will assume that all deaths are uniformly distributed in 1 year. The second one is constant force of mortality, and we will find some nice expressions with that assumption when we estimate the probability of surviving t time in the future, but now this value of t is less than 1. And there's also the hyperbolic assumption, which again is just assuming that everything behaves as with a different shape. Okay, so we're going to discuss all these approaches, but the first and the second one are the ones that I personally like the most, and I think are really straightforward to understand. So the first one is the uniform distribution of deaths, and it is in the name. So essentially, if we have like survivors at age LX, or essentially at age X, and then we have survivors at age X plus 1, we can get the total number of people who died. Remember that we have this expression for life tables, okay? And essentially, if we get this number of people dying, this assumption essentially is telling us, okay, if you have 12 members of your population dying, that means that in each month, one of these individuals die. So essentially, if we want to estimate something in the middle of the year or for some fraction of the year, we can do that, just assuming that this is happening in a uniform manner. So essentially, if we want to estimate those who are still alive at age X plus S, now S is between 0 and 1, not 11, just 1. We can get this as an average value, or essentially using linear interpolation or realizing that this is a straight line between LX and LX plus 1, okay? So this is what I just told you. Between X and X plus 1, what we have is this thing, okay? So essentially, what we're saying here is, okay, so this is 0 and 1, and we can locate the value of S at any point between 0 and 1, right? So let's say that I decide to estimate this value. So essentially what this is telling me is, okay, you are going to wait, or we're going to take into consideration how far you are from hx and hx plus 1. So essentially, you are departing from hx in this proportion, and you are this close to hx plus 1. So if we work with this expression, essentially what we have at the end of this expression is 1. Sorry, it's not a 1. Come on. It would be Lx, then Lx times S, then S times Lx plus 1. So from here we have this Lx by itself, and then we have the common factor is S, and we will have Lx. Which is defined as dx, right? So that is the reason we have this expression right here. So again, this is just, again, assuming that this is a straight line, it's a straight behavior. So again, we can just realize that this is a straight line with the slope being the number of people dying. Essentially, I'm gonna be changing my survivors for these many people or these many individuals at this stage. Of course, this is only true for between ages X and X plus 1, because then, for instance, if I continue this model, probably the next straight line is gonna be something like this, and then the next one is gonna be probably something like this. And we will have different patterns of different shapes. But in small intervals, that is something that we can actually do. So the interesting thing here is that this is Lx plus, I don't know what I'm doing. Okay, this is the line. So essentially, we are able to estimate Lx plus S as the original number of survivors, and then subtracting S times ds. So this is a big S, it's not a subscript, it's a regular value or number. So now, if we want to estimate the probability of death for people between ages X and X plus S, remember that S is less than 1. So this can be between ages 22 and 22.9, whatever. So we just have to remember that this is 1, well, the complement of this is 1 subtracting the probability of surviving. And this probability of surviving, we know the general expression is Lx plus S divided by Lx. And now, this is the reason we define the previous thing, because we can replace the number of survivors at age X plus S as those that we have at age X, and then subtracting S times the number of people who are dying in that year. And here we can just work this operation. So we will have 1 minus 1, that these two will go away, and the negative with the negative sign will become a positive sign, okay? So all these algebra and all these numbers, essentially what they mean is that under, and this is the way that we usually express it, under uniform distribution of deaths, what we have is the probability of some person surviving from age X to X plus S, where S is less than 1, is just S times the probability of dying in that, at that age or that year. Which, again, it simplifies a lot of the things that we're going to be doing. Okay, so questions here? I have, of course, examples, and we're going to be working on those examples right now. Now, this is my vaccination card. I don't want to lose that. Okay. So, what am I doing? I don't have the example here. Oh, yes, this is important. So more generally, this is something that we're going to find sometimes. Not only fractional duration, but also fractional ages. For instance, in this scenario, what we have is that S plus T, they don't necessarily have to be less than 1, but we're going to try to express these probabilities with that condition. So for instance, we can have 0.5 to X plus 0.25. And here S and T are meeting this condition. So we essentially, we will follow the same logic, and then this is the expression that we have when this happens. This expression down here. However, sometimes we're going to find something like this. Let me try to say, okay, 0. Come on. Something like that. So when we have things like this, essentially we can break this down into two specific things. So essentially, I can move the value that is greater than 1 to a different age, and essentially, well, we will have some example here. But the thing is, not always we're going to find that S plus T being less than 1, but we can have this option, and we will work around this. So in some examples that I think I have one example when this happens, so we can find a way around these things, okay? But once we have this expression with this criteria being met, we can just replace the value, our probability, using this expression, okay? Now, see this example. So for this example, we know that the probability of a person age X dying in that year is 0.1. Now, using this uniform distribution of deaths between integral ages, let's estimate this probability, okay? So this is the general expression that we had before, right? So we have 1/2 of QX plus 1/4. And just let me, okay, so we can use the general expression that we had before. Let me, we can use this, or let me show you one way to make this even simpler. Just if you don't remember that this is happening, or this is something that we can do. Okay, so we have this expression. The first thing that I would do with expressions like this is try to see what we can do, okay? So let's assume, let X just be 1. Why? Because we are going to try to find a way to do that. Okay. So essentially, this means that Lx plus 1 is Lx times 1 minus this probability, essentially, and this is 0.1, this would be 0.9. And from this, if I am assuming that Lx is 1 and Lx plus 1 is 0.9, this means that the number of people dying is 0.1. Okay? So this is the long way to estimate this thing. Now, let's go back to this probability. So 1/2 of qx plus 1/4 essentially is 1 subtracting 1/2 of px plus 1/4. Why? Because I want to get rid of this fractional h that I have here. And this essentially is 1 subtracting Lx plus 1/4. And here we have Lx plus 3/4, right? Here I'm just using the general expression for this probability of surviving. Now, according to what we just did, we can estimate this Lx. Remember that Lx plus s x dx. So this is something that we can work with this happening. So essentially this would be Lx subtracting 3/4 of the x, which would be 1 subtracting 3/4 0.1, and then Lx plus 1/4 and this is 0.927, no, 0.975. And with these values, we can estimate now this probability, right? So this would be 1 subtracting 0.925, 0.975, and this. Okay, so this is the long, the long version of this approach. As you can see, we can work around this thing. We can always find different things or different ways to to find things that we know already or that we define from the beginning, which is fine. Now let's use the short version of this expression, essentially the one that we have right here. So this is the long. Now, the short version. So essentially the short version of this means, essentially says that, okay, if you want to solve this, essentially, you will have to, let me write it up here. S Q x plus t x times qx So this means that this is 1/2 of qx. And we should get essentially the same value, or almost the same value. So again, which one do you think you're going to be using? I'm pretty sure you're going to be using the short version of this, but again, it is only like trying to work around these expressions and find things that we can use. And yes, the short version of the long formula, or well, the short version using the long formula is fine. But sometimes if you just don't remember, and you just remember this this association or this assumption that we have from the beginning, you can find a way to work around these things and try to rewrite this as this, or essentially reaching an expression that is similar to this, and then again everything should work. Okay, but again, if you go with the short version, you should be fine. So this is working. Oh, there's another example here. That's a nice thing. I thought I only had one example, but no. Okay, so if we have this fractional ages assumption, remember that the first finding that we have was that this probability of death is S times QX, which is going to be really easy to use down here. But also this comes from the fact that LX plus S is LX, subtracting S times DX. So this is the key finding of this assumption, but this is the main approach that we're using. Essentially, this is where it comes the uniform distribution of deaths. This is where we are using that, but this is just a consequence of this thing happening. Okay, so if we have this question, well, it is really easy to work with this, because we know then that if we want to solve this, essentially this means that we have 0.4 times 1 minus P40, which is 0.419994373. Again, I don't know this number, but you can work this number out. Now, if we have this, again, we can go with the short version. Remember that this is S, and here the value of T is 0.2. And we have S Q X plus T, meaning that S equals 0.4 and T equals 0.2. And we can just solve this. Again, I don't know the value of that. So again, these are things that work. Again, I usually don't remember all of these approaches. I usually have issues remembering this long formula, but I remember this. I always remember this assumption, or this well, this property of this assumption, right? So I usually try to rewrite these expressions in order to find something like this. And it would be a really long way, but I think we have time. So let me, I don't know if I have enough room, but let me, okay, here I don't know if I can just make this thing smaller. It's different. Yes, I can. Okay. Now, so the long version of this problem, which again, I don't know the values here, you can estimate the values there. Let's only pay attention to the second one, because again, the first one is a direct consequence of this, so that's fine. So the second one is the one that probably, if I don't remember the long version of the formula, I will have issues with, right? So what I do, I always remember, or I always try to rewrite this as the complement, this. And then I can rewrite this using the general formula that we know. So it would be L would be 40.6, 40.2. But I still don't know what to do. But right now I can work with this expression that I have here. But if the only thing that I remember is this, let's say that the only thing that I remember is this, I am still not there, right? So I should find a way to change this. But there's a way. I'm just going to use L40 here and L40 there. Essentially, I'm using just one factor of 1 there. And this translates into 0.6, 40, and 0.2, 40. As you can see, I am getting to something similar to this, because from this expression now, I know that this is 1 minus 0.6, 40, and 1, 0.2, 240. And now I can use the one that I remember. And I should get something pretty similar to the values down up here. So can you help me estimating these values, these probabilities? The first one, so we have this, and then double check that this is almost the same. Okay, so let me change colors again. So this is 0.000108. And it should be pretty similar to the second one, because again, we're not changing that much. No. Okay, I'm back. I think I was gone for a few seconds. Okay, sorry. So the first one was 0.002108. Did you get the second one? I don't know if while I was gone for those couple of seconds, you got it. So it's 0. So it's almost the same. Well, yes, it's almost the same. And please just somebody estimate the last one. I think I'm just gonna change that. I don't have enough room here. So 2.108 minus 4, right? 1, 2, 3, 4. So this should be also. Yeah. So again, well, just double check that we actually get that. So we're getting the same values. We're getting something, things that are pretty close. And yes, it doesn't. We don't see the difference, and we shouldn't see the difference between the second part of the part B in the short or in the long version, because we're doing the same. I'm just working more in the long version, but that's because I just want you to know how to solve these things if you don't have access to the formula. So it's the same. But now, between the first and the second one, there should be a difference again. It's really small, and right now we don't see that difference. But remember that we're going to be working later in the semester with millions. Like we have this benefit that pays 10 million pesos or 10 millions, whatever. So again, those decimal values are going to result in a significant amount of money. Okay. I just realized that I'm in the other class. Well, that's fine. I can change it. Okay. So now let's see what happens with the other assumption that we have. The second assumption that we can use to estimate this is the, oh no, wait a minute, we're still on the uniform distribution of debts. So this is something that we can just, that we find that if we get the derivative with the time or the duration, which is S of this expression, we will just have the probability of debt. Why? Because remember that this SQX is S times QX, and if we get the derivative for S, essentially we just end up with QX. Okay, so that's the reason this happens. And we can estimate the probability density function. We can estimate a lot of things. The density function essentially, which is this, it will be, again, the same way that we have been working these things now. The probability times the force of mortality at this specific time, which again, nothing to be worried about. Okay, now, the second assumption, and I think I like this one better, but again, there's no preference between one or the other, has to do with, okay, so let's say that we don't have a uniform distribution of debts. Let's say that we have constant force of mortality, just like that, just because what we are going to do is, okay, in this small interval, we can assume, or we can use the assumption that this happens, okay? So what we will have at the end of the day is that the probability of this happening, well, in general, the probability of a person surviving 1 year of age is e to the negative value of the integral between 0 and 1 of this thing, okay? Now, if we know, or if we are under the assumption that the force of mortality is constant, if we estimate the probability of a person surviving from age x to age x plus s, what we will have is just this integral of a constant, which again, we don't have to solve, is e to the negative power of mu times s. And because of the functions, the properties of the exponents, we can rewrite this as this expression. And guess what? What we have here is just this probability, right? So essentially, probably a better way to write this would be px to the power of s. So this is another assumption. This is another perspective. We can use this to solve the same issue that we had before. If we have fractional ages or fractional durations, we can use this approach, and again, it will be valid. Okay. And so let's see what happens with the same example that we had before. So we have this probability of death, and now we know that the force of mortality is constant between integral ages. So this is our assumption. Instead of having uniform distribution of deaths, we have constant force of mortality. So let's estimate this probability of death. As you can see here, I didn't give you one general expression for what happens when we have fractional age. We know what to do with fractional durations, but that's fine. We can change these into things that we know, okay? So this would be this, and this would be 3/4. And now what I can do here is I can use the same trick that I used before. Let's just divide up and down using this LX. And now we can use what we just have, right? So let me do this. So essentially, 3/4 this being px this power, and 1/4 this. Okay, I'm back. I don't know what's happening with my connection. Okay, so okay, so we are here, right? So I didn't kind of I wasn't talking by myself, right? So we were all here at this point. Okay, just let me know if I need to repeat anything. No? Okay, thank you. Okay, now we have these things, and again, what we know is that this is 0.1, but again, this is not complicated because then we know that this is 0.9, this power, and this is going to be 0.9 to this power. So this means that 1/2 of qx plus 1/4, that'd be 1 subtracting 0.9 force, that's 0.9 1/4. So let's estimate that. This is 0.0513. Now we have a difference from the other, from the previous value, because in the previous example, or when we use the uniform distribution of debt, let me change colors. This is just like a note here. So on the uniform distribution of debts, what we got for this was 0.05128. And now we're essentially we're getting the same, but just let me, that was 128, and this was, let me use another decimal, 131. Well, even 132 if we notice that after that we have a 6. So here we have differences, okay? So which one is correct and which one should you use, or are we going to be using? It doesn't matter. So essentially, well, unless I ask you to use one of these approaches during the exam. So if I ask you, okay, use uniform distribution of debts, then you should get something like this, and then you should follow the process that we already did. Or if I ask you, use constant force of mortality, then you should use this approach. One thing to remember is that uniform distribution of debts is associated with the value of the probability of debt. I don't know if I have enough. I can write it down here. So uniform distribution of debts means that this is this, okay? And constant force of mortality means this equals this. So one is with the probability of death, the other one is the probability of surviving, okay? But again, the two approaches are acceptable. If I ask you to use one, you just have to use that. But if, for instance, let's say that we're in the last exam. Now, remember, the last exam is on Teams. You get all the weekend to work on the exam. It's take home. And I ask you, okay, estimate this benefit with blah, 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 as for a fractional duration or for a fractional age. And you're solving that. And if I didn't tell you which one to use, you just have to let me know. Okay, we are going to be using this approach, and that's fine. You just have to let me know which one you're going to be using, okay? So questions in this example? Okay, perfect. Now let me see if I have another example for this thing. I think it's the same one. Yes, it's the same one. I don't know why. Yes, it is the same one. Okay, now let's work in the second example, but now with constant force of mortality. Remember that here we don't have a short version of this thing, but again, there's not a big issue. So this one, the first one is is really easy to solve because, again, remember that this is just 1 minus 0.4. Sorry, this is P. 40, which essentially means 1 minus P40 to 0.4. And you can solve for that. Now, this second one, again, we need to find a way to express this in terms of probabilities of survival, and then with only having fractional duration, not fractional age. And here we have fractional duration and fractional age. But again, we're gonna start the same way. Let me go down here. And we're gonna use the same trick that I just used. This is 40.2, which is L of, this would be 40.6 divided by L of 40.2. And from here, again, just multiplying and dividing by L40, this changed into 0.6 P40 and 0.2 P40. And now we can use our our constant force of mortality assumption with P40 0.6 divided by P40 0.2. So it's 0.999473. Okay. As you can see, we essentially get the same thing. So 2.108. I think before we have 82 and now we have 83, but that's fine. Right. So again, these things, and yes, a lot of these are really like probably straightforward, but you will find probably a couple of examples in the verification problems that you will have to do this and then change again the value and then change again the probability of death for probability of surviving, and then trying to change again in order to reach some expression that we can use. Okay. Now, the last assumption that we use is called the hyperbolic assumption. And this again comes from the fact that we can assume that this association between the fraction of the year or fraction of the time of survival that a person has is follows, instead of a straight line, just a kind of a hyperbolic approach. I am not going to develop everything, but this is the main assumption that we have. And as you can see, it kind of looks like the equation for the hyperbola. Is that the way to pronounce that? Whatever. The hyperbolic function in your geometry class. So that is the reason this receives that name. So after some algebra, essentially we reach these two expressions. The first one, when we only have fractional duration, is pretty similar to the one that we have, but now we have to correct for this assumption. And when we have fractional duration and ages, again, this being between 0 and 1, we reach this long expression. Again, these expressions are longer. Are they better? Again, the difference is going to be in the really, really low, really small decimal values. Well, not decimals, but in the decimal positions. Here we have 1, 2, 3, 4, 5, 6, 7, 8. So in the previous example, we have differences in the 8th decimal position, which again is pretty small, right? So probably nothing big is going to happen. Okay. So let's just again solve the same problems, but now using this hyperbolic assumption. Okay. True. So according to the hyperbolic assumption, I'm just going to write here the formulas, because again, I don't know these formulas by heart. I just need to double check my notes. Okay. So if we were to solve for this, we will be under the second scenario, right? Meaning that this will be 1/2 of qx, and then 1 minus 1 I think I can just 3/4 of qx, right? So 1/2 of 0.1 divided by 1 and as you can see, this translated immediately into the long formula for the first assumption, the uniform distribution of debts, just because we have this thing. So again, I don't know the value. What's the value that we should get? I don't have it here. Yes, I have it here. And now let's see. Sorry, I should wait. Should I move to the next one? Yes. Okay. So again, the same example, just because I want to use the same thing once and again and again. And the idea for me of repeating the example is that we will have the same information and then the results will be probably different. So this would be, again, let me write this again. Yes, the problem of using OneNote is that it's not easy for me to go to the previous page. But at least now I can write. So the first one is just this one, which would be 0.5, 0.4 of 1 minus 0.999473 divided by 1 minus, so this would be 0.6, 1.999473. And the second one would be this other option, right? So it would be 0.4 of 1.999473. 1. So 0.6 of 1. And I think I have the values here. Just double check, please, these values, because and this one is 2. So again, we have a small difference, but again, it's in the 8th decimal position, which again is pretty small. Chances are it's not going to affect our findings. The only thing that, again, you need to do whenever you're working with these things is just let me know which approach is the one that you're using. Okay, unless I tell you explicitly what to do. They're almost the same, Rodrigo, because again, this is when we have a live table. And when we have a live table, well, we could probably double check which one. Okay, we can do it right now. We have time. Yes. Okay. Don Hey Rodrigo, that was a very good question. So let me open my live table. Where is it? File, open. Okay. But this is with, oh yes, we can do it. Okay. My entire screen. Okay, so let's do the following. We have, what do I have in page 16? We have enough room. Okay, wonderful. So let's estimate, using the live table that we estimated last time, or that we have from last session. Yes, let's use 0.4 of 25.2, just like that. So let's estimate the probability that a person aged 25.2 years of age dies before 25.6 years of age, right? So now let's do it before 25.5. Just so it makes more sense that we can actually ask that. So 0.3. So essentially before being 25 and a half. Okay, so what can we do? If we use the first approach, the uniform distribution of death, let me find my formulas. Okay, so A, for uniform distribution of deaths, we will have that 0.3 cube the 25 cube to 25.2 would be 0.3 cube of 25 divided by 1, subtracting 0.2 cube of 25. Okay, so this is times and times, and we can we will see the values in our live table. Now B, under constant force of mortality, what we know is that 0.3 cube of 25.2 is 1 subtracting 0.3 p of 25.2, which is 1 minus L of 25.5, 25.2, and essentially this is 1 minus, I'm just going to change already divided by 25 here. So this would be 0.5 p of 25, p 0.2 p of 25, which translates into p of 25, 0.5 is p of 25, 0.5. Oof. And now let's on the hyperbolic, and let me write down this expression. The hyperbolic, I'm not going to write all the expression. 0.3 cube 25.2. This is 0.3 times cube of 25 divided by 1, 0.5 cube of 25. Okay, so yes, now we need to find these values in our live table. Okay, so live table is right here. And 25 is right here. Okay, so let's just do this. So the first one, I'm going to use Excel because I know I have all the decimals points in there. Okay, so it would be 0.3, 0.3 times this divided by just 1 minus, right? Times this. So this is the constant divider. For the second one, I need P to 0. Okay, I was so excited I didn't realize here it should be 0.2. So it's just 1. Okay. This 5 is 0.2. There you go. And the hyperbolic, this should be pretty close to the first one. Okay, so here we have our 3 probabilities of death. Okay, well, for that, for those ages. So now, how can we double check, or how can we see which one is the closest one to the reality? So let me, I'm just gonna change this life table here. Okay, yeah, sorry. I get so excited when somebody asks questions like this. So this would be, let me double check, table 2. Okay. Because we only need to estimate this value. And 25.2 as well. I couldn't tell you, I couldn't tell. Honestly, this is the first time that somebody asked that. I really don't know. We should probably double check. And also because of the values here. So I'm thinking probably if instead of having, in most examples, the value of S was larger than the value of T. But what if I have 0.1 or 25.8? So I think that might change the fact, because then we're playing with S and T in different positions. So I think it has nothing to do with the assumption, but it has more to do with where we are falling in the interval. Okay. So the thing that what I'm gonna do now, again, you don't have to do everything, but I'm just going to change, come on. I'm going to estimate this and this. I wanted to have these probabilities and this LX. So in reality, what is the thing that I needed? L25, okay. Okay, so this is the correct value. So this is using this is mayhem, right? Okay, so the thing is, we usually don't have the function. Right now, we have the function. We have the function that we use to estimate this life table, okay? But most times, we will only know the values in life table, and probably we don't even have the parameters from the function that we're using. So in this scenario, because we did have these values, I can do this. So what am I doing? Okay, which one is the smallest? Is this one, right? The UDD is the one that is closest to. So actually, in this example, the one that is like really going like having significant differences is the hyperbolic. So the best one would be the UDD. But again, look at the values that we have here. It's 0.0000007, and then we have the difference. So again, it's really the differences are really small. But again, this would be a way that we could tell which one is actually falling, like working better for us. So I don't know if this answered your question, Rodrigo, or just push me into ecstasies of estimating survival probabilities. Okay, so here the fact that, and I'm thinking probably, okay, all of these three approaches should result in the original value when we get to the value of 1. So essentially, if we have the value of S being 0, that would be, well, essentially 1, or 1, we would be having the following probability of death. So I think it's not probably which one is better in general, but probably depends on, first, the shape of mortality that we have, then where in the interval, and that would be a really good question. Probably that is a good honors project for future students. But essentially, that would be a good question. So how far in the interval? Probably the uniform distribution of deaths results in the same difference along the interval. And probably the constant force of mortality provides better estimates when we are getting close to the limits of the interval. In the middle parts, probably is not. And then probably the hyperbolic is resulting in something different. So I don't know. I think, and here I'm just throwing out hypotheses that I'm just coming up with. So, but again, we could double check this, but remember that we will have to do this in small intervals, and probably there's a way that we can double check this, but again, I am not going to ask you to do that, but that's a good question, Rodrigo. Well, more practical, I will go with constant force of mortality. At least for me, that's the more practical. Again, because for me, it makes more sense what we are doing. It makes more sense that, okay, let's assume that in this small interval, force of mortality is a constant. So essentially what we are doing here, what we are doing in that constant force of mortality, again, if we have a function for mu x that is, okay, so if I have my force of mortality being like this, what we are doing essentially is just, okay, so let's create this stepwise function. And this is in a 1 year interval, okay? So again, I know what I'm doing. I know what my problems would be. The biggest issue would be in the really older ages, because what I'm doing, like here, when the function is not growing that fast, again, so having a stepwise function is not probably resulting in big differences. But when this force of mortality starts growing exponentially, then of course these steps are going to start falling like further apart. So probably we will have to pay attention to what is happening there. And probably for this, approaches, I can assume that UDD is better. So again, I think it's not in a general perspective, but it's more what ages you are considering and how far in the interval you are, right? So probably if you are here, your error is going to be significant, but if you are here, it's not. Okay, sorry. Now you give me something to think about. I'm going to have dreams with these things now, but thank you. Okay, so any other question? Yes, another question, or yes, you're making fun of me because I'm going to be dreaming about these things. Okay, all fine. Okay, so